This is the last video that I have prepared for Chapter 13, and it's probably also the least academic, the least detailed, may leave some questions to the imagination, but I wanted to include it because it involves what's called the heating value of fuels. And that is something that I used a lot during my engineering practice. So I had not been exposed to this in thermodynamics class, but I was exposed to the idea of the heating value of fuels when I took an undergraduate class in power generation. So back in 1974, 75, there was a senior elective called power generation, had to do with power plants, primarily hydrocarbon fuel based power plants. Had a wonderful instructor who told us a lot about the ins and outs and showed us how to solve problems associated with power plant operations, power plant design, and power plant performance improvement. And one of those things was the ability to simply provide some engineering estimates for the heating value of various hydrocarbon fuels. This is just an example. So this has to do with your Chapter 13, Section 2.3, enthalpy of combustion and heating values. And in that section, as you browse it, you will see two terms. One is LHV and one is HHV, lower heating value and higher heating value. And I found this little image I clipped out of the internet of images, and after doing a little studying on it and adding a couple of labels myself, you can see, imagine that someone has provided a test company, a testing service provider with some fuel. Let's say perhaps coal, so a sample of coal. And that service provider has analyzed 7 samples of coal using a calorimeter and some various experimental methods. And for each sample has plotted to provide back to the person of interest values for the HHV and LHV, the higher heating value and the lower heating value of these 7 samples. And they're plotted, and this is just an example of some fuel that's been analyzed. So you can see that in general, the higher heating value, whatever that is, we'll talk a little bit more about that in a second. Whatever it is, it's slightly higher than the lower heating value. Okay, you've got that. And the units are kilojoules per kilogram, or in the English system of units, BTUs per pound mass of the fuel, heating value of the fuel. Okay, pretty easy to understand. There's just some common sense that would tell you what that might provide to you. Now I'm going to go to your textbook and just clip out the text from section 13.2.3 regarding enthalpy of combustion. And a synonym for the enthalpy of combustion is called the heating value, just the words heating value. And it's this H bar RP, reactants to products. And so you can see it's the same sort of familiar block of terms, the sum of N leaving, H bar leaving, minus the sum of N in, H in, the reactants. And I'm not going to read the text to you. I'm going to try to summarize the text in the next slide to let you know, to give you a feel for what's the practical application of the heating value described in your textbook. First, HHV. So the higher heating value, HHV, what that does is that assumes that the H2O in the exhaust. So remember, the exhaust products of any combustion are CO2 and H2O. And you've been through this thermodynamics class enough to know there's different phases that H2O can exist in. It can exist as a vapor or gas, or it can exist as a liquid, can it? Okay. And do you remember that there's a big enthalpy difference between H2O saturated vapor and H2O saturated liquid? You remember numerically, no matter what the pressure is, there's a big numerical difference. H sub G is a much bigger value in kilojoules per kilogram than H sub F. Well, the higher heating value assumes that the H2O in the exhaust is condensed all the way down into water. And so that some of the heating value is explained by the energy that you pick up by condensing the water. It's like it's about 800, 900 BTUs per pound mass. Wow, that's kind of a lot in the whole scheme of things. The lower heating value assumes that the H2O in the exhaust remains at a vapor. And your common sense concept tells you, yeah, that sort of makes sense, because when you look up, right, when you look up at an exhaust stack, you don't see water pouring out of the exhaust stack, do you? You see that it's pretty much vapor coming out of the exhaust stack. Now, you can see a plume of white substance, and that is definitely that white substance would be H2O liquid, right? Because vapor you can't even see. And so that cloud, the white cloud, probably is some measure of H2O liquid, but it'll be a mix, right? So you know there's going to be a saturated mixture in between saturated vapor and in between saturated liquid. So somewhere in between. But recognize, big picture here is HHV is a number, BTUs per pound mass or kilojoules per kilogram, assuming that all of the H2O in the exhaust is condensed down into water, liquid water, saturated liquid. LHV, that's also a number, kilojoules per kilogram or BTUs per pound mass, assuming that all of the H2O in the exhaust is remaining as vapor. In other words, almost like a clear exhaust. Okay. Now back to the real world and where we live. It turns out that HHV, the higher heating value, is commonly tabulated in commercial literature from the United States. It turns out that lower heating value is commonly tabulated in the literature, in commercial literature in Europe as lower heating value. That kind of blows my mind. And when you delve into the literature, particularly commercial literature, you will see that the heating value is simply titled heating value. Sometimes it's not common to hear higher heating value is blah, 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 or lower heating value is blah, blah, blah. So just be aware of that. Just be aware that in the United States, commonly tabulated quote unquote heating values are quoting higher heating values. Okay, so you say, well, so what? What good is this to me? How does it relate to my thermodynamics class? You may be given a problem where you're asked to find the heating value of a fuel in BTUs per pound mole, or BTUs per or kilojoules per kilomole. If you go to table A25E or A25 for the SI units, you will find a handy column for these fuels called higher heating value and lower heating value in BTUs per pound mass. BTUs per pound mass. If you're asked to find BTUs per pound mole and you have BTUs per pound mass, how can you get BTUs per pound mole? Gosh, I think what you would do would be, well, let's see, if you know the molecular weight of, let's say, methane, molecular weight of methane is 16, right? Pounds per mole, you would multiply, I think what you would do would be, let's see, pounds mass per pound mole times BTUs per pound mass. You would multiply these two numbers together, 16 times 23,880, to get some huge number of BTUs per pound mole. Simple as that. So that's kind of a cool result in your textbook of heating values, both HHV and LHV, for specific fuels. Okay, very handy. You say, okay, well, that's great. How does this relate in the real world? This is an example of a spreadsheet that I came up with in the real world in my working experience, comparing the heating value of various fuels of a whole bunch of a real mixture of fuels. And so how would you compare and the price of each one? Now, if you scan the prices, you're going to see that the price of fuel is lower than it is nowadays. But this is what the price was when I did the work. But you'll see that how can you compare the value of different fuels for heating value? Well, you would determine the value in the dollars per common unit, which must be million BTUs or kilojoules. Cost dollars per million BTUs. And that's what you're seeking to do because it's money out of your pocket. And you might be studying which one of these fuels should I buy if I want to generate heat. And this is where this higher heating value, lower heating value really comes in handy because engineers are in no mood to spend hours and hours going through that detailed Chapter 13 first law analysis to determine the heating value for a certain proposed situation, when in fact you can get a tabulated higher heating value or lower heating value, tabulated, if you look closely, it'll say for complete combustion. And so this is the way I came up with my comparison of what's the most expensive, what's the least expensive fuel or source for heat. And one thing, so I'll show you. So for example, kerosene, $23.97. If you want to use kerosene for heating, like a kerosene heater, compared to firewood, about $14 per million BTUs. So if you're interested in saving money, your common sense might tell you that wood is cheaper to heat a home than kerosene. Common sense would tell you that, but here you can quantify it. You can do an economic study with numbers to verify that it's cheaper to heat with firewood, hardwood firewood, than it is to heat with kerosene, and on and on and on. And sort of the interesting thing is you look at wood pellets. Wood pellets are more expensive to heat with than firewood. It makes sense. A wood pellet is a manufactured product, but you get the idea. And let me scroll back a little bit. Okay, I don't see it here. Don't see it here. But here it talks about. Here's the text in your textbook. It says the enthalpy of combustion, H bar of RP, in other words, the heating value is defined blah, 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 when complete combustion occurs at a given temperature and pressure. So you see, that's a little, it does say that you have complete combustion of your fuel. That's good. It doesn't say anything about whether you're burning with pure oxygen or air. So your Chapter 13 knowledge should say, well, that would be a difference, wouldn't it, in terms of adiabatic flame temperature or heating or heat release. But do recognize that this heating value term with complete combustion, not saying anything about excess air or oxygen only or burning with air, it gives you a good, quick, and dirty method for quickly getting tabulated values for heating values so that you as an engineer might continue on to do an economic study of lots of different fuels and not go into that Chapter 13 detailed analysis. So I just thought I needed to throw that in, certainly needed to define higher heating value, lower heating value. I got that from my power generation class as an undergraduate. You may or may not get that in your thermodynamics class. And so what's the takeaway from this module? Well, there are lookup values available for higher heating value and lower heating value in that table A24. It eliminates the need for detailed combustion calculations to estimate the heat release. It's not exactly science, but it's a good engineering approach when you're comparing fuels and you're trying to figure out what's the relative dollars per million BTUs or the relative dollars per kilojoule when I'm trying to study the selection of different fuels. Okay, so as you see, not very scientific, just depends on some tabulated values, but you can get a lot of bang for your buck, make good use of your time when you're on your day job, rather than going in and doing the detailed calculations in Chapter 13. Now, don't get me wrong, there are many, many applications, of course, where you must go to Chapter 13 and do those detailed calculations for adiabatic flame temperature. Let's say for designing equipment, for equipment design, you must be able to get in there and determine the adiabatic flame temperature, where the heating value is really not going to help you very much in that regard in terms of determining the adiabatic flame temperature. Okay, so I hope I've given you at least a starter kit in making mechanical engineering calculations for hydrocarbon fuel combustion.